I'm recording this. And by the way, congrats that Dogecoin is going up. Hopefully you don't lose money anymore. All right, so today we will talk about how do you program and how this program is stored inside the memory and how do you actually run the program, right? So the quick recap. If you want to store something in a computer, everything is just in binary, right? Which has a value, so just a bunch of ones and zero, right? Basically, anything that has a text, this is convert to binary. Number, oops, my bad, number. So convert to binary. Sorry, I've been driving for so many hours today. Same lecture for both day, yes. So there was a question that was what time? 5 p.m. to 7 p.m. Basically, this is supposed to be lecture one. Today, I basically went to Grom Tidin to transfer the ownership of the land to me because I'm buying a house and I just got back actually. So I need to cancel and move the section 1 class to tomorrow. And I kind of like one of the nice thing about that is basically if you are trying to do in-class exercise or if you want to try assignment 2 and you have questions, you can attend tomorrow lecture basically to ask question on Discord. Treat it as like super extended office hour where I'm going to be there to making sure everyone can write code in C. There's a few other things I would recommend. I'll say that toward the end of the class, but basically that involves like try to use GDB and try to use this other thing called wall grind. It would check for allocation errors. Basically, it would try to help like fixing or give warning about your code. Yeah. Not sure what my cat wants.
I can hear the cat.
Yes.
I can hear your cat.
I know. I am not sure what does he want as well because I just fed him. I think he just want attention. So basically, if you have number, you can basically represent in binary. And yes, that's Meow behind me, and there's one cat right here and one cat behind. Yes.
Excuse me, I got a question. So the class for tomorrow, it's going to be the same lecture as today.
Exactly.
Yeah.
But
okay.
But after the lecture, so we should have about 1 hour or more left where I'll be on Discord. So if you have questions, just join Discord when we have like this cluster of people inside the voice channel. I'll be there to answer your questions. Yeah.
Okay, thank you.
Yep, no problem. So basically, if you look at number, these are convert to binary. These include integer and floating point, right? By the way, if you hear the cat toy and if that's annoying, let me know. I'll kind of like mute the cat toy by hiding it for now. Then if you say, hey, data is actually just ones and zero, right? It means that you can store those data inside the memory. What is a memory exactly? Basically, think of it as like a matrix that store ones and zero. Your program, which is in binary, right? Program is somewhere in the memory. Your data is somewhere in the memory as well. Everything is inside. When you run something, right? When you run something, the program basically would run, get issue. Basically, you allocate, you book an area inside your DRAM saying, hey, that's your memory for the program. If you go into like more advanced class in the junior and senior year, in the architecture class, assuming that's one, and I'm teaching that, I'll basically tell you how does that, how does it work? How does program run? How do you actually find the first line, go to the next second line, go to the third line, etc., etc. How do they actually access the data, right? You can read and write from the data, but that's kind of like the high level overview. Everything is binary, ones and zero, and everything will be stored in the main memory. There's also different data type. You have character, you have integer, you have floating point, and you have what else? String, right? Which is just an array of character. You have also complex data type where you can do a struct. And you have this thing called pointer, which is a useful tool where you can access the memory location for anything, including the program, right? So we talk about how to represent data. We talk about bits operation, right? Which we will do some practice today in the in-class exercise. But how about a program? How do you actually represent a program? To go through that, I kind of need to do a quick recap on what is a computer, right? So if you want to understand what is a computer, what is that? Actually, let me redefine what is a computer because we got a pretty interesting definition, which are all correct. The last time I asked this question in the first lecture. So now that we talk about Linux and C, it is a big calculator. Awesome. Essentially that's what it is, right? It's a big calculator. It's done in the processing. The processor side is process your data. Think of it as a function that takes input, produce some output, right? In the middle, now we learn your program and your data is in this memory. Whatever size you have in the program in the machine, right? Some machine have 16 gigabytes, some has 32 gigabytes. If you don't want to buy the new machine yet, you end up with 4 gigabytes, which you're gonna hang a lot. As one of you might have realized, I'm joking, but yeah. Wait, right? Maybe I put in the wrong slides. Let me double check. Sorry, there was a question about whether lecture 9 is the same as lecture 8 slides, except for the first page. So let me double check what's on Canvas right now. I'll be back in about a minute, just going through my desktop. It should be different, actually. Let me check what's lecture 8 that you can see. This is kind of weird. Oh, okay. Let me unpublish this. There are 2 lecture 9s. My fault, sorry. Let me unpublish the old slide that was from the previous semester. So we are actually running a little bit ahead compared to last semester. Okay, so let me refresh and make sure that's the only thing that show up. Yep, so the only thing that says lecture 9 program representation, that should be the slides here today. It should be on Canvas now. If you download the wrong one, I'm so sorry. Please go and download the correct one right now. And make sure I throw this further away so my cat just run out of the room and will fetch that back to me. Okay, so you have a computer. It is a big calculator, right? We now learn that if you have a memory, basically your program will be stored there. Your data will be stored there. And this is where every single thing that's running on your computer will actually book a LAN inside your memory to actually run the program. Then you have I/O. What is the I/O? It's input and output. It literally stands for input/output. This is how you interface to the computer as a human being. You type things on a keyboard. You send packets in and out throughout the network. These are all I/O. You install the hard drive. Hard drive is also included as a part of the I/O. It's not a part of the memory, right? So these are how computer is organized. There's a connection between the program inside the memory as well as the data to the processor. These are the bandwidth, right? And you can see the bandwidth is smaller on the processing side and higher on the I/O side. They also take different amount of time. It's fast. This is really slow. So if you go into the next class when you try to optimize your program. Make sure you optimize or minimize anything here. The more you have to touch the storage element, the slower your program will have to be basically becomes. And that includes the network as well. These things are super slow, right? In fact, if you actually go to like high performance computing area, they actually put data somewhere in the processor. They try to make sure you never actually leave the CPU, and your program will be extremely fast, right? So that's how you can write a fast program. Why do we? Oh, that's a great question. So that's a question that whether the I/O from the keyboard represented as an electric signal. Yes, actually. If you take out the keyboard button, what do you see? Anyone here has a mechanical keyboard where you can actually pop out the button? Every keyboard you can actually pop those things out, right? And I do recommend every maybe 3 or 4 years do that once in a while. It's nasty down there because how many people eat while you're typing? Also, how many people drink soda while you're typing? I do both. Yep, everything that becomes the particles just go down on your keyboard and it's actually hidden underneath that. So when you clean it, it actually makes sure you don't have like possibility of having ants down there. I see my colleagues having that. It's nasty. Don't go there. So yeah, tidbit. If you pop those things out, you see like copper surface that touch the and then on the bottom side there's also another one. Basically you push the button, you make the connection, you actually close the circuitry, right? I mean it's electrical signal physics way back in your high school. Oh yeah, so if you own a laptop, don't do that. I'm talking about actual keyboard. Don't do that on your laptop. I'm so sorry. Your laptop, underneath that is your motherboard. Don't pop it out. And also that would also break your warranty for your laptop. So yeah, just make sure you don't do too many disgusting things like eating and drinking soda and like kind of like spray everything around your laptop keyboard. Yeah, such is life. So if you see those connections, it's actually wiring, right? When you hit the keyboard, it connects the circuit. So it sends electrical signal saying, hey, you hit the key, I don't know, letter D, followed by the enter key. These are electrical signal. And then this electrical signal will be sent through the I/O, right? And the operating system, you know through the driver, right? When you install driver, what are they? It's a piece of software that drives the hardware that you just bought. For example, a video card driver is designed to drive the video card to make sure they run what they're supposed to do, right? So the keyboard is usually is a part of the motherboard driver, and whenever you install the OS, these things are simple enough for every single OS to handle this. So it know, okay, you're hitting these keys, you're sending these signals. What will happen next depending on the program? The OS would basically, the driver would notify, hey, the user typed this. In Microsoft Word, if you type in letters, you just show that letters on the screen, right? Because that's basically a text editor, so you're typing. If you are playing Dota, for example, you type QWER, basically you say, hey, I'm going to use the skill 1, 2, 3, and 4, right? If you type R, just using the ultimate, assuming you use whatever the default config and you're not like me who are too old and we play like the older version of Dota, so we never use that one. You just use the older ones, right? Depending on the config, depending on the program. If you are playing first-person shooting and you type in ASWD, what are you doing? What would the program do? ASWD just move you around, right? So that's basically how each program takes in this electrical signal and interpret it different way. If you're in Google Chrome, if you type control, So it has a signal that someone is like holding the control signal plus N. It would also send another signal, say, hey, someone want to create a new window, right? So these things, typically they are called interrupts. These interrupts, it's the signal that get raised up. It's like someone raising their hand, hey, I'm typing control N. The program that are running will listen to this interrupt and it would know what you're doing. That's a super high level how to implement these things. You have such a fun time doing that in the OS class. Basically, we will implement how you would handle these things in OS. These days, I think that's another good comment. So basically, these days, the comment is you can imagine if current laptop or desktop doesn't have the GPU. Actually, I think they will not function properly. Most of if you look at the old motherboard, like really old one, like Intel Pentium 2 or 3 generation. Some motherboard comes with a video like onboard video chip. There is that all. So they come with the onboard video chip that used to drive the monitor. So you can use the onboard, kind of like a GPU, but it's a super light version of GPU where you can play like YouTube video and that's fine. But you can't render any game. Otherwise the computer would cry. Literally like the fan would like burn, like basically would like, the fan will turn on to a really high volume. These days, have you heard about on-chip GPU? It's also so there's another comment from the student. Basically, is this similar to the bottleneck situation? It depends, right? Basically, you're rendering the video card. The computer, which has a CPU, can do everything on the background and also on the foreground. User can still see the changes. It just your monitor might lag, right? Your monitor might be, hey, I'm not gonna refresh at 60 hertz, 30 hertz. I can't catch up. So you can see some laggy movement, right, on your monitor. So if you buy a CPU these days, more CPU comes with the on-chip GPU. These are designed. These are. I'm sorry. These are designed. I'm so sorry. He jumped too quickly. I'm like, I cannot catch him. These are designed so that you can run a simple video graphic workloads, such as yes, jump scare in the class. Well, hopefully no one here is scared of cats driving around the monitor. These are designed to run the simple graphic video. There's other things like YouTube video running MPEG-4, making sure you can run basic games. Like if you play SimCity 4, you play Dota, I think you can run with a medium setting these days. And if you play first-person shooting game, you probably will die because you like it'll be too loud. You can't react to the AI who's basically everyone shooting at you, right? So these are the on-chip GPU, but some of them come with a really powerful ones as well, right? So that depends on what you're looking at. The new, so for example, MacBook, right? It actually does have its own like powerful GPU. Your iPhone also has a relatively powerful GPU. That's why you can actually play a lot of like crazy games with like really beautiful graphics. If you're interested at how to look at the specification, definitely check. Like if I can help, I'll definitely check with me. I have a thesis on how to design a GPU, so yeah, it kind of stemmed from the fact that I do play a lot of games and I want to figure out how this thing works. Regardless of that, right? So yes, if your laptop is what you described to me back about 2 lectures ago, yeah, most of the latest smartphone will be faster than your laptop. Regardless of that, unless you're buying, I think, the new Ryzen chip from AMD, some of them doesn't come with a GPU because they say, hey, you really, if you want to a desktop, right, and you buy this CPU, it makes so much more sense to have a dedicated GPU. Because if you buy a dedicated graphic card, most of the time you're not using this onboard on-chip GPU. You use the off-chip one because it's so much more powerful, right? That drive your monitor. And actually, you can use it to mine like Bitcoin. I don't think these days you can mine Bitcoin and profit from that because you pay too much money just from your electricity bill. But it's a really powerful GPU. So AMD say, hey, if you're gonna buy that thing anyway, we will actually take the GPU out from our chip and use that extra area for something awesome for the CPU. Right? So you can make a more powerful CPU because you have more area. And then you can use the GPU off chip, which is it can be any of the NVIDIA or AMD GPU. So these things are also like what is going on your computer, right? So the GPU is a little bit different. They kind of interface through the memory because people in the system community and people in the architecture community saying, hey, if you treat these things as a part of your CPU compute stack, it's not gonna there's so much overhead, right? That are running, right? So the GPU now has its own like processor from the software point of view. It just run everything on its own. I'm going super sidetracked here. I actually forgot how we got there. But if you look at a computer these days, processor talk to the memory, talk to the I/O, right? This processor can be integrated GPU plus the CPU or just the CPU. Right? How do you talk to the computer? Now let's go back to the context of this class so that folks don't get too overwhelmed and like going into random direction. So let's refocus. All right. There's this thing called instruction set architecture or the ISA. Think of ISA as human language. That's one for English. English language has its rule, right? If you want to refer to something about the future, you say, I will. It's a future tense, so you know that's something about the future. It's a grammatical rule. I went to Gom Chidin, right, to buy, basically to get the deed for my house. It means that I did that in the past. I am teaching. It means that I'm basically teaching right now, right? So these are rules in human language. The ISA has the same thing. It's a list of commands. It's a predefined rules that human design. So we as a human being design this thing. How many of you heard about the ARM ISA or the ARM chip? MacBook, it had that. AMD is driving another effort to come up with a server-grade ARM processor. Most embedded systems use ARM, right? At least the more complicated ones. It's actually really power efficient. So this is the ISA. It speaks in ARM ISA. If you get the chip that is built in with Intel x86 ISA, you run the program designed for ARM. Intel chip is like, what the heck? Because I don't understand the language. It's like if I put you in a room where the lecturer speaks German, you'll be like, what the heck? I don't understand anything. So it's the same concept here. Each chip is designed for one language and one language only. The compiler will compile, basically it will translate the program which are all in human language, or I mean, assuming that we can understand what program your friends is writing, right? So if you say int main, you know that, okay, that's the main function. It's the first line of your program, things like that. Compiler take that, process it, spit out just tons of binary that is representing for each ISA, depending on what chip you run. You can actually take the same program, compile it for x86 processor, which is your desktop, your laptop. Let's say your friend buy this new MacBook that use the M1 chip, which is ARM, right? what you can do is you have two choices, basically. You can emulate, fake this until basically have a translator. In a human term, if you want to talk to a German person who cannot speak English, what do you do? Is Rosetta too. So what do you do if you want to talk to another person who can only speak German? You can do two things, right? You learn the language, or you use the translator. Yep. So you use a tool. The compiler can learn how to compile in German language, or you use a translator. Somehow we call it emulator. It emulates the machine language in ARM, right? So if you are talking to more like a hardware side of things, there are two. So the obvious terminology, hardware, the piece of hardware you buy. The microarchitecture is the actual implementation of your design. Let's say you design a chip. These are microarchitectural design. It's similar to the architect, right? My job, like when I call myself a computer architect. What I would tell people what I do. Essentially, what I do is similar to the normal architect job. I look at the rule set by mechanical engineer and civil engineer and say, hey, don't build the house this way, it will collapse. Make sure you build the house this way. There's a rule book for that. The same thing goes for circuit. I'll take those pieces of hardware, I'll put them together, and voila, you have a house. So now you have a chip, you have a computer, right? The processor that you buy is essentially the ISA or the language and the hardware. Right? The language and the hardware, it processes your program. Right? It processes your program. Why do we care? Anyone want to program in zeros and one? I'm pretty sure no one wants to program in zero and ones, right? The ISA, what it does, I guess the ISA plus the compiler, if you look at it in a really, really high level abstract sense, it takes your program, which then spit out just ones and zero that do the exact same thing as the program. Assuming there's no bug in the compiler, it would do the exact same thing as what your program described, right? So it allows you to translate a problem into the solution in the program into machine language. So this filled in the black box. So hopefully it's more clear now. You run a program, how does it work? Because if you look at the circuit, everything is just a ones and zero. What is the missing component? The language that translates into the language for the machine, and the tool that translates programming language into the language for the machine. The language for the machine is an ISA. The tool is a compiler, right? Yeah, you got a program. So, still, this means that you kind of need to know assembly to some degree, because you sometimes there's bugs in your program and you want to make sure what's going on. You want to figure out what's going on. So knowing how to read the assembly can be useful, and that's where we're going next. It's painful, but I can assure you it's way better than zeros and one, right? So let's get sidetracked now. We have a discussion about the language, and I guess this is kind of like motivate the design of the programming language. So there's this thing called semantic gaps. Anyone here heard about the word semantics? A long pause is good. It means that this is new. Anyone heard about the word syntax? So you might have seen syntax before. When you compile the program, the syntax error, and you're like, I don't know what syntax error means. In language, in human language, that's a grammar, right? It's a rule that you need to follow. If you don't follow that rule, the sentence will look super confusing. That's syntax. It's equivalent to syntax. It's the rule set by the language that you have to follow, right? If you don't put semicolon at the end of your statement in C, it would yell at you, syntax error, I need that semicolon, right? So that's syntax. What is semantic? Yes, basically. Syntax error is I don't know what you're trying to tell me what to do on that particular one command. For that one command. What is a semantic? If you read a paragraph in English, you will know the meaning of what that paragraph is doing, right? Each paragraph has a meaning. And if you have 7 people reading the same paragraph, they should get the same meaning, right? So that's semantic. Each program has a semantic where you can know that, okay, that's a program to do matrix multiply. That's a program that do a sort. It sort the array from smallest to largest. So these are the semantic information. It's not syntax. You can have a program that correct syntactically is compiled, but it has no meaning. It do some weird thing that has no meaning, right? So semantic is the information revolving around what the program is doing. There's a gap, right, between the software you're writing to the ISA. And you can design how big that gap you want to be. You can have a language, the ISA, right, the assembly that has a super large semantic gap where the command in your assembly would control, say, logic gates inside your processor. It would control send this bit from here to here, send this bit from here to here, and that can be painful, right? But it leaves a lot of room for the compiler to translate your program into this super fine-grained language that control electrons. Okay, so that's a large semantic gap with the ISA. And the compiler people will probably kill the person who designed the ISA. That's too much of a task, right? So you can have the inverse, small semantic gap. ESA would look almost like a programming language. There's a command to load value into an array. There's a command to sort an array. There's a command to do a matrix multiply, for example, right? This allows more application-specific optimization. You can do a lot of things in hardware. You can have an instruction that do, hey, train this in the model for machine learning. One instruction, and you have a special hardware to handle that, right? So that's possible. It depends on how you would like to design the hardware. So we're going into a little bit more like a hardware design philosophy here. And you can just make sure you're aware that you can translate one ISA into another, right? Basically change the semantic gap. It can be done both in hardware and in software. But what happens if the ISA change? Computer, as I said, cannot understand executable or the exe files, the binary files that compile with a different ISA, right? If you, as I said, if you compile a program for ARM processor and want x86 to run, it's like, okay, I don't understand what you're trying to do. The compiler will actually recompile the program and re-optimize for the new ISA. Or you can do a code transformation, which is basically changing the binary from one ISA to another. So in conclusion, right, in the world, that's why you don't have so many ISA. It's annoying to have so many languages. Think about it this way. Let's say you have this magic language that human can speak and is optimal, right? You can express whatever you want to express. It's perfect and it's easy to learn. Would you like to make sure that's a universal language? Yeah, right? It's annoying for me to have to learn English. I have to learn Thai, even though I know it's pretty useless outside of Thailand, right? Who would care? I might have to learn Chinese in the future. I might have to learn Japanese, right? If I want to watch a lot of anime. I might have to learn, I don't know, like if I am in the United States, there's actually a lot of people who try to learn Spanish because there's a lot of a large group of people who come from Mexico who speak Spanish, right? So learning new language is annoying. It's a lot of work, So you don't want that many ISA in most cases. Think of human language, right? So now that we talk about language, any questions so far? Because we kind of almost done with the lecture, actually. Now I just want to kind of understand the overview of how computer operates and talk to each other and talk to us as a human being, right? So if you look at assembly code, by the way, if you have questions, feel free to type in. I'm basically reading those questions while I'm saying things here as well. So the next thing you might want to figure out, like, so I talk about the language. What should I go in there? So let's talk about a normal human language. In a sentence, what should be in a sentence? Can someone tell me if I say something, one sentence, what should be in there to make it meaningful? A subject, obviously, yes, right? You need to know who is doing what. And a verb, because it tells you the action, right? And sometimes you can have an object, which is who get the effect of the action, right? So we can have subject, verb, object, and some adjectives, adverbs, right? The same thing, right? The same analogy goes to computer language, especially the ISA. If I say A equal B plus C, basically what I do is I'm going to take a value of B, take a value of C, add them together. That's a verb, right? I add them together. That's a verb. That's a command. Who get the result effect? A is like I got the new value, right? The same goes with computer language. Inside the instruction, there's this thing called opcode. Opcode is the verb, is the command. It's the command. You want to specify what the command do to the subject and the object. So these are addressing mode, data type, instruction types, formatting, right? So these are some of the things we'll go into in the next lecture, but understand it's just subject, verb, object. You're doing something to something else, right? So basically in general, right? Oops, my bad. Going too fast. Instruction would consist of opcode. This is kind of like the verb. That's also the operand. The operand are basically those subject slash object. It's specified I'm going to add B to C. So B and C are the operand. A is the operand. The opcode is add, right? So use a different ink color. So B, C, and A. These are the operand. The add is the opcode. I want to add these two things and write the result into A, right? You can also do something with the memory because that's where you have to interface to your program and to your data. So you have a way to, okay, this is a character. I just want to access 1 byte. This is an integer. I want to access 4 bytes. This is a long integer. I want 8 bytes. That's alignment as well. Which byte do you want? And then there's a virtual memory management, which we will not talk for now. We'll talk about that toward the end of this semester. What else can go into the ISA? For completeness sake, these are handled inside the OS class, but you can talk about calls and interrupt. These are dealing with things like keyboard. If there's a network packets coming in, right? You want to browse the internet. Search Google Chrome, right? You search something. How can you, is it possible for me to guarantee the results would come within, say, next 1 millisecond? No, right? It depends on how fast your network is. A few days ago, True went down. I want to search something on Google Chrome, it never arrived, right? So these are things that are unpredictable and the program has to handle. Chrome has to say, hey, I can't reach there. There's no internet connection. It has to actually tell me what's going on. You have to deal with the I/O. You have to deal with thread management, who get to run on the CPU, right? So this also goes into the ISA. And by the way, no need to memorize any of this. Each language has its own manual, and those are free. Then when you go online and check the manual, and instruction is the most basic element between the software and the hardware. Everything in your program is an instruction. And as I said, there's an opcode and the operand. The opcode is the verb. The operand is the subject and the object. So let's say I say add R0, R1, and R2. This is like some random assembly that I came up on my own. I just want to say add R0, R1, and R2, where it means I'm going to add R1 and R2 and write the result into R0, right? In this case, right, R0 is the operand. Oh, sorry. In this case, R0 is the operand, R1 is the operand, R2 is the operand, and the plus sign here is the operator, right? If you think about it in a really abstract high level, this is super simple. And I will always tell my students, hardware is stupid. So everything has to be simplified. It's really stupid. So you have to kind of like, at the end of the day, everything becomes just like series of command where the way you construct the command can be complicated, but the way the hardware takes command and run it is simple, right? Why simple? It's efficient. It's actually less costly, right? So that's how we design the hardware. We want to minimize the cost. We want to minimize the energy. So a lot of time when you look at assembly code, it's actually simple commands, but one by one, it can be long to just do a program that say A plus B or a Fibonacci. That can be long. It can be a few lines of assembly, right? So that's it for the class today. So I hope this kind of like give you a little bit more insight into the hardware world, as well as more insight into what the heck is assembly, right? It's just a series of commands that represent your program. In the next lecture on Thursday, I'm gonna actually begin with a review session. So the assembly would come next week. Why do I want to do this? Because assignment 2 is out. I want to make sure we do a review session at least a week before your midterm, which is next Thursday, right? So you have more time to prepare. So first of all, we'll go over some exam questions that you might see on Canvas already. It's from the previous semester. So if we go through those questions and you have something you want to ask away, right? Make sure that when I go over the exam questions from previous years, it's on the 16th. What day is today? Maybe I'm wrong. It's on the 16th. Okay, I'm so wrong. It's 2 weeks from now. I'm sorry. 5. It's on the 16th. Okay. Let me write it here. Exam on February. All right, sorry, my life is hectic. I'm sorry that I gave you most everyone here a heart attack. It's on the 16th. Is it okay if I do the review so that we can also cover things like what's in the assignment 2, and I kind of like ask you to try some of the question in assignment 2. So it'll be like mostly programming, and it'll be like mostly on Discord. Is it okay? We can do a quick review right before the exam as well. So we can do like spend an hour if you have like last minute question from assignment 2 and things like that, right? So let's do this. Let's have a few review session. The first review session is this incoming Thursday. Why do I do that? Prepare you for assignment 2. Prepare you for how the heck you write program in C. Prepare you for what else can you run into for the exam. So we go over some of the exam questions. It's kind of good time because we kind of wrap up the C and Unix and Linux, right? So come with questions. We also cover assignment 2. I'll enforce, not try, but I'll try my best to like, hey, let's actually try assignment 2 in class. So if you have questions, you can ask me because you can actually finish assignment two really quickly if you know what you're doing. And the fact that I'm in that like session allows me to tell you how you should proceed with assignments, right? And then today, that's basically it for the lecture slot. We have 4 in-class exercises for the past couple of weeks, including today. So let me stop the recording because that's basically the rest are just, hey, let's go do our in-class exercise. All right, so let me stop right here.